And it's more of a refresher than anything. So we've seen a whole bunch of integrals that have that log form, where I'm talking about log form as the denominator's derivative is the numerator. That's what I mean when I say log form. That's not like a formal expression. But it feels to me like we should have a formal expression for it because we see it so frequently. So when I say an integral is in log form, that's what I mean. The derivative of the denominator is in the numerator, and anytime we have that log form, we integrate to natural log of the denominator. Natural log of the absolute value of the denominator, more precisely. And the Zamboni, why do they choose to ride the Zamboni right when class starts, or during class every different day? So we have 6 trigonometric functions, and we know that sine and cosine integrate to each other essentially, but the other 4 are all going to integrate to some sort of natural log. And if something integrates to a natural log, we should be saying, oh, well, we must be able to go backwards and put it in log form. If it's going to integrate to a natural log, we probably can put it in log form. So let's go ahead and just remind ourselves that tangent is sine over cosine. And okay, it's not quite in log form yet, but we can do a little bit of massaging. What does the numerator have to be to make this log form? Yeah, negative sign. So we're just going to put a negative there. We put the negative there. And so now we have -1 out in front, multiplied by an integral that's in log form. And we know that that integral is going to integrate to natural log absolute value of cosine plus c. And quite frequently, you'll see this integral in a slightly different form. We also know that this exponent has superpowers. It can fly up into this exponent position inside the log. And the effect of an exponent of -1 is that you flip the base. So if we were to flip the base, it would come up inside there. And if we flip cosine, we get secant. So you could write this in either form. Both are completely legit. Does not matter. Either form is fine. So cotangent. We write cotangent. Again, let's write it in its sine and cosine equivalents. So here is the equivalent expression with sines and cosines. And how about that? Is that in log form? Does it have to be manipulated? Yeah, it's in log form instantly. Derivative of sine is cosine. So that's log form. And whenever we have log form, we get natural log absolute value of the denominator plus c. All right. And we are going through this primarily for this one, because we are going to see that one a lot. We've already talked about what the antiderivative is of it is, but I want to do it again just because it shows up so frequently. So we have secant, and what we know just by looking at like the integration tables is that it integrates to a log, and so we have to sort of figure out what we can multiply it by to turn it into a fraction in log form. And what I suggested to you last week was to think about the derivative of secant. And we know that the derivative of secant times tangent. And I just use that as a memory tool to remind myself that, oh, I'm going to multiply top and bottom by something that's almost the derivative. Instead of secant times tangent, if we multiply by secant plus tangent, that's actually going to put this in log form. And we'll see this pretty easily. In the numerator, we're going to distribute that secant. So we're going to end up with secant squared of x, and then plus secant times tangent. And in the denominator, we have secant plus tangent Is that in log form, or is it close to log form? It is in log form. The derivative of secant is secant times tangent. The derivative of tangent is secant squared. So it's in log form. All right, the derivative of the denominator, we have two terms, so we just differentiate across, derivative of secant and derivative of tangent, and it matches the numerator, so it's in log form. So this is the one that we are going to see quite a bit this semester, so it's probably going to get to the point where you just write this down. If you see this on an exam, you're more than welcome just to write that down. You don't have to go through the step there, but that's how we prove that the antiderivative of secant is in fact that. Multiply by 1. It's our little trick of multiplying by 1. So now this one's a little harder, cosecant. So we're integrating cosecant. The idea, of course, is similar. If you look at an integration table, you see that it integrates to a log, which then leads us to think, oh, can we manipulate the integrand and make it so that it's in log form? And the answer is yeah, we can. Now, if we do something similar to secant, we probably will be able to get there. So let's think of the same memory trick. Let's say, oh, what's the derivative of cosecant?
Negative cosecant cotangent.
It's negative cosecant cotangent, and we have some flexibility here. So it's negative cosecant cotangent. If we just sort of peel away the negative sign, we could just do this. And this will work. So instead of secant plus tangent, we'll do cosecant plus cotangent. If you want to be a stickler for that minus and say, ooh, let's put a minus in front of both, that's also going to work. It's not going to matter. You'll be able to massage it a little bit. So if we do this, let's see what happens. So we get cosecant plus cotan up and down, top and bottom. So let's distribute. And we're going to end up with cosecant squared of x plus cosecant cotangent of x. All that's divided by cosecant plus cotangent. Now this is not quite log form, so that minus is going to come into play here. So you could put it in front of these two and these two, and then you'd still have to do a little manipulation anyway, so it doesn't matter which way you go. So let's think about what we need here. The derivative of cosecant, we said, is minus cosecant cotangent. So we have to get a negative up here. So if we multiply the numerator by -1, then we also have to multiply the outside by -1. If you put your minuses in here originally, and you put your minuses in the denominator, you can think of it as factoring out that minus from the denominator to get it into log form. So either way, you're going to have to do a little manipulation. So now this is in log form, though. The derivative of cotangent is minus cosecant squared. So now we have it in the form we want. This one is not going to show up a ton. You don't have to have this one memorized. I would probably put this one on a note card, though, because that just comes up so much. So this is going to be negative, so -1 on the outside, natural log of the absolute value of the denominator, plus c. And there's some ways to fiddle with this. You could turn it into sines and cosines and pop the -1 up top, but this is fine. We don't need to do a bunch of log properties. Any question on log form? So looking at this again, we just want to get into the habit. This pattern is so common, it just has to be one of your reflexive integration techniques. Is it in log form? Can I put it in log form? Because it shows up so much. Super important. Last Thursday, we did integration by parts with a twist. And we're going to look at a classic integration by parts with a twist. This does not look like a typical integration by parts with a twist. Remember that when we did integration by parts with a twist, in our mind, the ones that we did were the integral of something like e to the x cosine, and e to the x sine. These were the two that we saw last week. That, there was two functions, both of which had derivatives that were sort of repeating themselves. But this one actually is an integration by parts with a twist too. Bless you. This is kind of a classic one that you see in all the Calc 2 stuff. They love this example. Now, when we do integration by parts, we are separating the integrand into a u and a dv. The dx always goes with the dv. And my suggestion to you all is pick the biggest piece up here, the most complex piece, I think we've said is a better word, the most complex piece that's easily integrable. And so when we look at secant cubed, there's only a couple of ways we could treat it. We could treat it as secant times secant squared. We could treat it as secant squared times secant. Like, there's not a lot of ways to break up that secant cubed. And what we know is that the biggest chunk there, the most complex chunk that's easily integrable, is if we put the secant squared with dv. Because we know that the integral of secant squared is tangent. So if we integrate this, we're going to get tangent right there. And now certainly we could have put secant there. We just saw that the integral of secant is natural log of secant plus tangent. We could. But we want to pick the most complex piece of this that's easily integrable, and that's secant squared. And then over here, we are going to get that du. The derivative of secant is secant times tangent. I didn't leave myself much space here, times dx. So sectan times dx. All right, let's see what happens. Now I'm giving you a heads up that this is with a twist. So whenever we're doing the twist, we need to use some sort of letter, usually a Greek letter, or doesn't matter, you could use a capital I, whatever. You need some sort of letter to represent the original integral because we're going to be doing some algebra in the long run. So the original integral, we're now going to do our integration by parts, our ultraviolet voodoo. So we're going to have secant times tangent. So that's UV, ultraviolet, minus the integral of voodoo. Voodoo is the bottom row, so that's going to be secant times tangent squared of x dx. So there is our first integration by parts. All right. So now we've come to an integral. And remember, we always ask ourselves, is this integral easier than the one above, or is it harder? If it's harder, you went the wrong way. If it's easier, you're going the right way. If it's about the same difficulty, it's probably going to be a twist. And so when we look at this, it's about the same. It's still not ideal, but we have what we have. So we have a product of secants and tangents. And we talked on Thursday, I think it was Thursday, maybe it was Tuesday. If we have products of secants and tangents, we had two cases that we really looked at carefully. If secant was to an even power, we pulled off a secant squared with the strategy of letting u be tangent. The derivative of tan would be that secant squared that we pull off. If tangent was to an odd power, we pulled off a secant times tangent with the idea that we'll let u be secant, so that the derivative of u, the derivative of secant, would grab that secant tangent that we pull off. This is neither. right? Secant's not to an even power, tangent's not to an odd power, so it's neither. And the strategy, if it's neither, is to generally use the Pythagorean theorem and rewrite one of them. And that's what we're going to do here. So we're going to rewrite tangent squared. We have that cool identity, which hopefully you have down pat by now. We know our secant tangent identity really well. That image tells it to us. 1 plus tan squared is secant squared. So let's try that and see what happens. So we have this stuff out in front. And in here, we're going to have secant of x and then tangent. So tangent's that vertical side, so it's going to be the hypotenuse squared minus 1. So the hypotenuse is secant squared. So that's secant squared of x minus 1 dx. And let's do a little distribution. So we still have this lingering stuff out in front. Oh, look, we're going to have an integral of secant cubed of x. So secant cubed, and then minus an integral of secant. This minus has to distribute, though, so if we break it apart into two integrals, that's what we have. So secant cubed, but a negative, and then minus secant, but we distribute that minus to make it plus. So that's what we have. Well, that's what the original integral was. So now we have an algebraic equation. On the left we have omega. And on the right, this is minus omega. Right, the integral of secant cubed, that's what we said omega was representing. Plus, we've just seen the integral of secant is natural log absolute secant plus tangent. We've got that. Now we're ready to twist. We've got an omega on the left, we've got an omega on the right. We're going to twist them together. That's going to give us two omegas on the left. And we have a subtle step here. As soon as that omega vanishes from the right-hand side, we need to introduce a constant of integration. Because embedded within that omega is an indefinite integral. So in that omega, there is a plus c. And so if we add it to the left side, we want to make sure the right side has a plus c. Question?
Where'd the negative go? On the top to the second row?
So this negative here distributes.
Oh.
So this is secant cubed minus secant, and that minus becomes minus secant cubed plus secant.
Yeah, makes sense.
So that minus distributes to each part. And what's our last step? Divide by 2. So this tells us what omega is, which is what our goal was. So if we divide by 2, we are going to have our antiderivative for secant cubed. We also had a reduction identity that you could use for secant, but again, that's not really math. That big old reduction identity. That big old reduction identity is not worth memorizing. So there is our antiderivative. Questions? That all makes sense? So this idea of introducing this omega, works really nicely. Kind of reminds me of, I can't remember if we've done this semester. Did we talk about, we all know, let's just go back to numbers for a minute. We all know that a repeating decimal is rational or irrational?
Irrational.
A repeating decimal is rational. If we're in the land of decimals, a non-repeating, never-ending decimal, that's irrational, like pi and square root of 2 and square root of 3 and square root of 5. Right? Those decimals have no pattern, but they go on forever. Those are irrational. If we're in the land of fractions, a rational number can be written as a ratio. Right? That's what a rational number is. It's a ratio of integers. So if you're looking at that decimal, you're like, oh yeah, that's rational. How many of you know how to turn that into the corresponding fractional form, into its ratio form?
125 over 999.
How many others know that? Couple? Anyone know how, maybe if you don't know that it's 125 over 999, does anyone else know how to get to it?
Try start from 1 and multiply that by 1, 2, 3, and so on and so forth, all the way to infinity, and see what works.
That is a method that could be time consuming.
We'll get there.
We have a better method. So this is in algebra. What's the first letter that comes to mind if you're in an algebra class? X. So let's let this equal x. And what we want to do is notice that we have 3 decimal places as our repeating pattern. So we're going to multiply both sides by 1,000. And if we multiply both sides by 1,000, this side becomes 125.125 repeating. And then we break this apart. The decimal point acts, really, it's kind of like an addition. And we're adding this. And so what is the next step?
Well, X is just that.
X is that thing. This is very similar to that integration by parts with a twist that we just did. We now are turning this into an algebra 1 equation. Same that we just did with the omega. Same idea. So that's why it reminds me of this. And all of a sudden that 999 is coming jumping out at us. If we subtract x from both sides, if we subtract x from the left, this is the fun stuff in algebra that's barely ever taught anymore. Then we have that. So that's how we get to our fractional form. That's how we get to our rational form. So you pick off the repeating part, multiply by whatever you can do to break it apart, and then back substitute in the x for the repeating part. And that gives it this. So that's how we do that. Yeah. Good job knowing that. You might be the first person that I've heard spit that out so fast in, I've been teaching this class like 28, 29 years. That's impressive.
I wouldn't have figured that out though.
How did you know that then?
The 9's trick works for
The
everyone.
the 9's.
5 over 9 is 5 repeating. 50 over 99 is 0.50.
Point. Yeah. Okay. Okay.
Keep adding nines.
Uh-huh. Yeah, that's clever. Nice job.
I've heard of that, I just never actually saw why
Yeah.
it works.
Yeah.
I just know that it's a trick that works.
Yeah. Yeah. That's the math behind it, which
Completely forgot about
is amazing. That in Calc 2, that's really a simple algebraic problem, but most of you, if you haven't seen it, have totally forgotten it. That's how that type of problem is usually on the SAT. It's on the ACT type stuff. Okay, so let's go to probably the most difficult integration technique that we are going to see, and that is trigonometric substitution. So trigonometric substitution, we are going to do it in a slightly modified way to what the book does, for a good reason. It will require less memorization. Less memorization is usually a good thing. And I'm going to try to just break this apart into 3 cases. And I want to name for each of those cases because we're going to refer to them back again and again and again. So having a name for each case is going to be really convenient. So this first case is sum of squares. There's only, the other two cases have a minus. So if we say sum of squares with a 1. So it's not a squared plus x squared, it's u squared plus 1. It's a sum of squares with a 1. Sometimes in math they'll say with unity. Unity is another word for 1. So we have a sum of squares with a 1. That's going to be our first case. That's going to be the simplest case. That's going to end up being the arctangent case. Okay, so sum of squares with a 1. And the other two cases are going to be difference of squares. And I'm going to refer to this as a difference of squares with a leading 1, and this a difference of squares with a trailing 1. So that's how we're going to refer to these. So difference of squares with a leading 1, and this is going to be difference of squares with a trailing 1. Now, if you look in the integration tables, you're always dealing with a squared plus x squared, or a squared minus x squared, or x squared minus a squared. So they don't force this one thing. And my suggestion to you, you can do it either way, my suggestion is that if you do a little bit of algebra first to make these ones, it's going to be easier in the long run. So that's the case. If you're a contrarian and you don't want to do that, that's totally fine. But there's less memorization. If we can remember the 3 basic cases, it's going to be a lot easier in the long run. So if we can reinforce some algebra and do 3 basic cases, we will be good. So these should be looking like Pythagorean identities. Let's go to this slide here. So here, if you look at this Pythagorean identity, 1 plus tan squared is secant squared. That should be jumping out as, come on, highlighter, work. That. Sum of squares. So 1 plus tan squared is secant squared. So if I told you that u is equal to tangent, if u was equal to tangent, what would 1 plus u squared be equal to? Secant squared, right? If u was tangent of x, then 1 plus tangent squared would be secant squared. And this gets at kind of our strategy. Our strategy is that we are going to have a sum of squares or a difference of squares, and what we'd like to do is collapse them into one term. So if we think about denominators and integrals, if we have 2 terms, we can't split the fraction. If there's a 1 plus say x squared in the denominator, we can't split it apart. If the 1 plus x squared is in the top and we have a singleton term in the denominator, yeah, we can split the fraction. So the basic strategy is that we've got 2 terms, a sum of squares or a difference of squares. Ideally, if we could merge them into one term, then we have a lot more flexibility. And that's what trigonometric substitution is essentially doing. If we have a 1 plus u squared in the denominator, if we were to let that u be tangent, then we'd have a 1 plus tan squared, which could be turned into a single term, secant squared. So that's the idea. Second one, if we take sine squared plus cosine squared equals 1, and we rewrite it, we have a difference of squares with a leading 1. So if we had a 1 minus u squared, if I told you that the u was sine, then you would say, oh, we have 1 plus sine squared, which can be collapsed into cosine squared. So again, taking two terms and smushing them into one. And the last one, if we take the tan and the secant identity and rewrite it this way, now we have a difference of squares with a trailing 1. So if we had that thing in our integrand, and I told you, oh, let's suppose that u is secant. Then you would say, oh, well, then we have secant squared minus 1. And secant squared minus 1, if you look at your identity, secant squared minus 1 is tangent squared. So that, again, has that effect of taking two separate terms and smushing them into one, turning them into a single term. That is going to be our weapon to get at these integration by trigonometric substitution problems. So, the only three functions that we will ever use for trigonometric substitution: sine, secant, or tangent. Those are the only three. So integration by trigonometric substitution, always sine, secant, or tangent. Could you use the other three? Yes. If you want to be super, clever, you could absolutely use one of the others. But sine, secant, or tangent, those are the three that will always work. If you just get those three down, you are golden. Sine, secant, or tangent. So we will use tangent for the sum of squares. We will use sine for the difference of squares with a leading one, because 1 minus sine squared is an identity. And we will use secant if we have a difference of squares with a trailing one. We'll use secant. All right, so it all boils down to sines, secants, and tangents. And again, there's the two pictures of those identities. And here are the basic three that you need to know. If you know your basic three and you know how to do reverse chain rule, that's all you need. You don't have to memorize the A, like with the ones in the integration tables. If you go back to the integration tables, you'll have a 1 over A out in front for the inverse tangent, and then an x over A on the inside. And for the inverse sine, there's no 1 over A on the outside, but then for the inverse secant there is. You don't have to memorize any of those special cases. Where does the A go? That's always the complicated part if you're trying to memorize the general formulas. Don't memorize the general formulas. Just know the basics and know how to do RCR. That's all you need. That will do it for us. So you do need your basic three, though. You've got to have this as your foundation for integrals that turn into inverse trig functions. You've got to have those three down. And like I've mentioned probably too much, this one is going to show up the most. You just see it all the time for lots of different reasons. So that one is the one that you are going to see the most. Inverse sine you will see second most. This one you see mostly in homework and quizzes where you have open notes. I wouldn't put that one on an exam of knowing how to do that. You have to do trigonometric substitution with secant, but memorizing that one is the least important. These two, essential. All right, so how do we do this? So there we go. We look at that denominator, and we see a difference of squares. So the primary flag that you're looking for that says go trig sub is when you see a sum or difference of squares. Now there's times where you have a sum or difference of squares and you can integrate it a different way. Like if we just had the integral of 1 minus x squared, you wouldn't want to use trigonometric substitution. If you have 1 minus x squared in the numerator, you would just use the power rule. But if you're seeing a sum or difference of squares in the denominator somewhere, that's really your ticket to say, oh, trig sub, that's the flag, sum or difference of squares. Now, again, my suggestion is that we go with a sum or difference of squares with unity, a sum or difference of squares with a leading or trailing one. All right, that's going to be, in my opinion, the most strategic way to get at these things. Much less memorization in the long run. So, but you have to know how to do algebra. So, right? So if we want to force, if we want to manipulate this so that in the denominator we have a difference of squares with a leading one, we need to factor the 4 out. Right? We want to make that a leading one. The 4 needs to be pulled out. It needs to be extracted. It needs to be factored out. So that 4 is going to be factored out. And you may say, oh, well, there's no 4 in the x squared. How do I factor out a 4 when there's no 4? We make one. We make one. We conjure one up. Yay, we are so powerful. Right, so there is what we're going to do. We're going to conjure up a 4 like that. Now we have a 4 that's common to both terms. This 4 right here is now common to both terms, and it can be factored out to the front. Simple enough? At least it looks simple. So here is the next step. That 4 is being factored through a square root, so it comes out as a 2. And is it in the numerator or denominator?
The denominator.
Denominator, right?
One
We're
half.
down in the basement. So it comes out as a half, like that. And let's see what's left. So what's left is the square root. That 4 got factored out of itself, so we get a 1. And we're going to be left with 1 minus x squared over 4 dx. And we want one more algebraic step before we're ready to go. We want a difference of squares. That is not written as a difference of squares. If we want to write this as a difference of squares, in this denominator we want to write it as 1 minus x halves quantity squared. Now it's written as a difference of squares. That is not written as a difference of squares. So we do that. And now we are good to go. Now we've got it in the right form so that we can use trigonometric substitution. So, sine, secant, or tangent. Those are our only 3 choices. Tangent starts with a t, which looks like a plus. We always use tangent for the sum of squares, because 1 plus tan squared is an identity. If it's negative, it's got to be sine or secant. And so we ask ourselves, if we were to replace this x over 2 with sine, can 1 minus sine squared be turned into a single square? Yeah, 1 minus sine squared is cosine squared. Right? 1 minus secant squared is not an identity. Maybe I shouldn't say it's not an identity. It's not a good identity. Because what is 1 minus secant squared equal to? Not quite. Not quite. 1 minus secant squared is
Tangent squared?
negative tangent squared. And if that's in a square root, you have a square root of negative 1,
Imaginary.
which we don't want to go there.
Yeah.
Don't want to go there. So 1 minus sine squared should be jumping out at you as cosine squared. And secant squared minus 1 is going to be tangent squared. So here we have a difference of squares with a leading one. We're going sine. So here's how we do trigonometric substitution. We are going to let x divided by 2 equal sine of theta. That is our substitution right there. X over 2 is sine of theta. That turns this into 1 minus sine squared, which turns into cosine squared, and the square root of cosine squared turns into cosine. All of a sudden, we just have a single term in the denominator. That's our general strategy, is to compress that denominator. So now we have to do what we always do with substitution. Now we have to take the derivative of both sides here. Right, we have to turn everything into thetas. So we take the derivative of both sides. So here we get 1/2 dx. The derivative of the right is cosine of theta d theta. So now we're going to use these two to replace everything inside that integral. We'll worry about the limits of integration after we get all the guts replaced. So we have a half out in front, and then the integral. So in the numerator, that's where I'm going to target first, we have x squared. Well, if we look at our substitution step, if we multiply both sides by 2, we have that x is 2 times sine theta. So x squared.
4 sine squared.
Yeah, exactly. So we're going to say, okay, x is 2 sine of theta, and if we square it, we're going to get 4 sine squared. Once we multiply it all out, all right? And now here, if you have terrible notation, and you are one of those people that your math teachers keep telling you, don't forget the dx. You need the dx. The dx and the integral come together. If you are one of those sloppy people that just drops the dx for, I don't know what the reason is, you're going to be in trouble with trig sub, because that dx has to be also replaced. And if we look over here, dx is 2 cosine of theta d theta.
You also have already a 1/2 dx if you just pull the half.
And we could, absolutely, if you see that you have the half dx, you could replace the half dx, the dx over 2, with that half out in front. That would absolutely work. Otherwise, we just write it all in and it will come out in the wash. So dx, we're going to replace that with 2 cosine of theta, and the d theta will be in there. So that's that part.
Over cosine.
And then, down in the denominator, we'll write it out in gory detail this first time for sure. So this is going to be 1 minus sine squared of theta. Now let's deal with the limits. We have 2 choices. Turn them into thetas, or wait and go back at the end. With trigonometric substitution, if you convert them right now, you're going to be dealing with inverse trig functions. Inverse trig functions from the unit circle, if that causes you any anxiety at all, which it causes most people some anxiety, it's just easier to go back at the end. So it's easier for most people to just say, hey, let's use some placeholders. We'll just put a couple of placeholders in. We'll put some stars or whatever you want to use as placeholders. Don't figure out the theta values. We'll convert back to x and just deal with it at the end. Most of the time for trig sub, that's the way to go. Most of the time, it creates less opportunity for mistakes. Because as soon as you start doing inverse sine of root 2 and inverse sine of 0, I mean, those are easy enough, but that tends to be a place where you can make silly mistakes. So let's just go back to the x's in the end. So we put some placeholder limits in there, and then we're going to start simplifying. So here we're going to wipe out the 2's, and we're going to simplify what's inside here. So we're going to just leave these placeholder limits here for the time being. And again, in the numerator, we already said that's going to be 4 sine squared, so let's write that out. This is going to be cosine d theta on the outside. Down below, that's 1 minus cosine. That's 1 minus sine squared becomes cosine squared. Square root of cosine squared becomes cosine. Now let's analyze that for a moment, because we have to be a little careful. Because we know that the square root of x squared is technically absolute value of x. So we have to make sure that no shenanigans are happening. So when we look at this square, maybe I'll just write that, the square root of cosine squared, before we actually do it, just to analyze it for a second. So if you were to look at these values here, these values for x, we have these positive or non-negative values for x. If we were to substitute these in here, we would be doing inverse sine of positive numbers, which puts us in what quadrant? 1. So inverse sine is always an angle on the right-hand side. If you did an inverse sine of a positive number, you're above in quadrant 1. inverse sine of a negative number would be down in quadrant 4. So we're in quadrant 1. In quadrant 1. These put us in quadrant 1. Cosine is positive in quadrant 1. So the square root of x squared in quadrant 1 is x. So we do get just cosine. So let's write that intermediate step down then. And I will not try to trick you with that. The homework might try to trick you from time to time. So 4, and then we're going to have sine squared cosine and a cosine at the bottom, and of course they're going to cancel. But we're going to write out every gory detail this first time. So now those cancel. And we have an integral of sine squared, which we did like way back in the first unit. How do we integrate sine squared? We use a power reduction identity. So power reduction identity. So the power reduction identity is 1/2 times something. I'm going to pull that 1/2 out. So it's 1/2 multiplied, let's see, sine squared is
Sine of 2 theta, or 1 minus of
1 minus cosine of double theta. So it's 1 minus cosine 2 theta over 2, and the over 2 we can factor to the front. So sine has the minus sign, sine is negative, so 1 minus cosine of 2 theta. If it was cosine squared, it would be 1 plus cosine of 2 theta. And now we can integrate term by term, so we have a 2 out in front, and our integration of 1 gives us a theta. Integral of cosine, sine of the same angle, so the angle cannot change while integrating or differentiating, and then we do the reverse chain rule. The angle is a linear function, the derivative of that angle is 2, reverse chain rule for integration says divide by 2. So we get that, and we still have our placeholder limits. All right, we still have more work to do. Trig sub is the hardest of all the techniques because there are so many pieces to it. So, we need to get back to x's. Here's how we do it. First off, getting an expression for theta is easy. All we do is take the inverse sine of both sides of the original substitution. If we want to isolate theta, we need to pop that function to the left, which means invert it. It's like the e to the x and natural log of x. If you want to get rid of an e, you have to take a natural log. It's that idea. So we need the inverse function. You move a function to the other side of an equal sign with its inverse. So that's what theta is equal to. Now we have this sine of 2 theta. Over here we have sine of 1 theta. So the next step here, before we even plug in that theta value, we want to go one more step here. We need to turn the double thetas into single thetas with a double angle identity. So sine of 2 theta is 2 sine of 1 theta times cosine of 1 theta. 2 sine theta cosine theta divided by 2. We still have our placeholders. The 2's cancel here. So super important again. Your identities are going to be all over the place. We've already used a Pythagorean identity. We're now using a double angle identity. And these trig sub problems are complex because of that. We're always using identities to get through it all. All right, so we are close. Now we have one more thing. When you look at this u sub, or whatever, theta sub, trig sub, we have sine. We don't have cosine. We have sine. Here is the last step for trigonometric substitution. And what we want to do, and it will always work, is that we draw a right triangle as if it is in quadrant 1. And what we're doing is drawing a triangle that represents the relationship between theta and x. So where this is, every single time you do trigonometric substitution, you're going to get to this point, where you draw a right triangle in quadrant 1 and theta is that angle. And we want that to be true. Sine of theta is x halves. Sine of theta is x divided by 2. Okay, well if sine of theta is x divided by 2, this is the picture that represents that. Sine of theta is x over 2. Sine is opposite over hypotenuse. So there we have it. And with all these trig subs, we're always going to have one unknown side. And we find that one unknown side with the Pythagorean theorem. That's going to be 4 minus x squared, square rooted.
Hey, that looks familiar.
And that should look familiar. The missing side will either match exactly what's in the integral or really darn close. If you end up with a missing side that's 4 plus x squared, so it doesn't match and it's not close, something's wrong. Like it should match exactly or super, super close. All right, so, and now we know what cosine is. Cosine is adjacent over hypotenuse, right? Now we have all the trig functions. If there was a sine, a cosine, and a tangent, we just look at this triangle. Sine, cosine, tangent, right? They're all there. So this triangle is the key that gets us back to x. So that triangle will do it for us. So now we end up with, we have 2 multiplied by theta is inverse sine of x halves. Inverse sine of x halves minus sine of theta times cosine of theta. The sine of theta is x divided by 2. Cosine of theta is the square root of 4 minus x squared over 2. And now we're back to the original x's. And the original x's, I believe, were 0 and root 2. So now we're back. And in this particular case, we are still going to have to evaluate inverse sine. We still will have to do that. There are many times where you do trigonometric substitution, you can kind of avoid having to deal with inverse trig function evaluations. In this case, we have to do it anyway. And you could have done it up here with your limits and converted them. But in this case, we're still going to have to do it. But sometimes that part goes away, so you can totally avoid evaluating your inverse trig function. So it's generally better just to wait. You don't have to, but I see more errors doing that early than waiting. Okay, so let's get in the weeds here. We plug in root 2. So once again, you need to know your inverse trig functions. Inverse cosine is always an angle on top, 0 to pi. Inverse sine and inverse tangent are always on the right. So when we plug that in, we have root 2 over 2. We say angle on the right with the sine of root 2 over 2, and the angle on the right with the sine of root 2 over 2 is pi fourths. That is the angle on the right-hand side that has a sine value of root 2 over 2. So pi divided by 4. Pi over 4. And then we plug it in here, and we're going to get root 2 over 4. So minus, we get a root 2 over 4. And then let's plug it in here, and it looks like a square root of 2. So that's the whole antiderivative at the upper limit of integration. And then we plug it in for the lower. Over here, this all just turns to 0. If you plug in 0 right there, you end up with 0 times whatever, and that's 0. So inverse sine of 0. Angle on the right with a sine value of 0. Sine values are the y coordinates. So angle on the right side of the unit circle, or the sine value of 0 is an angle of 0 radians. So that everything becomes 0 there. So our final answer, if we distribute this 2, we'll end up with pi divided by 2 minus 1. There we go. Root 2 times root 2 is 2, so we have 2 over 4. That 2 distributes, we get 4 over 4, which is 1. So that is a classic integration by trigonometric sub.
Go back to the step where you're subbing in the square root of 2 with x over 2 and then square root.
So if the square root of 2 goes in here,
Yeah.
we get root 2 over 4. Right there, root 2 over 4. And when the square root goes into
Yeah.
the square root, square root
2.
squared is 2, 4 minus 2 is 2, so that's how we get that root 2. All right, let's go ahead and take our break now, because obviously these problems are not quick. Trig sub these are going to be the longest problems of the semester. Even longer than the infinite series problems most of the time. Substitution. So here, once again, the flag that sort of says trigonometric substitution is the way to go is if you see a sum or difference of squares and it's not integrable by other means. So we don't know how to integrate that already. That's not something we know how to integrate. U sub is not going to work because there's not a derivative of the radicand on the outside. So we can't just use U sub. So difference of squares or a sum of squares, we're going to go trig sub. And the strategy, again, that is the most efficient is to try to create this as a difference or sum of squares with a 1, with a leading or trailing 1.
This should be sine again, right?
So this will end up being sine again. So here we're going to factor the 36 out. So before we factor it out, let me just make sure it's becoming clear to everyone. In order to factor 36 out, we are going to think of, and as you do more and more of these, you will not need to write this step down anymore, but we'll do it the first few times just to make sure it's obvious. So multiply top and bottom by 36 for that second term. Now we have a common factor of 36 that can come to the front. That 36 can factor out to the front, and that comes through the root as a 6. So we'll have 6 multiplied by, let's see, we factored out a 36, so that's a 1 minus t squared over 36, and we kind of already know what we need to do. We want to write that as a difference of squares. We don't want to leave it as t squared over 36. We want to write it as a square.
You still need the integral sign, right?
And we still need the integral sign. Thank you. Yeah, good call. Oh yeah, I have the dt, but not the integral sign.
So you're that other kind of.
It's usually the other way around, right?
Yeah, all in the ceremony, you forgot both.
Forgot both. Must.
There we are, we're done.
That was so easy.
We
If you just change the problem into something you know how to do, that is a good way to get full credit. Full credit.
This is why you bring a white out, a bucket of white out.
Let's turn the integral symbol into a derivative or
I know.
multiplication by 0.
I know you can take a block pen, a very convincing block pen, and write a t right before the square root sign.
Yeah. Yeah, let's do that.
Just say not equal to.
Not equal
Yes.
to. It's true. It's not equal to. All right, so once again, Tanner said it, sine again. Difference of squares with the leading 1 is sine. Difference of squares is always sine or secant. We want to ask ourselves, is 1 minus sine squared the identity, or is 1 minus secant squared the identity? And the identity is 1 minus sine squared gives us cosine squared. So that is the identity that we are targeting. So t divided by 6 is going to be sine of theta. And if we take the derivative of both sides, or if you wanted to, you could isolate t right away. It doesn't, you can write this in a lot of ways. So here is our pair of substitution steps. That should replace everything inside the integral, if you still have an integral. So 6, I'm going to pull the 6 out. In here, we're going to have the square root of 1 minus sine squared. And that is exactly what we were trying to get to, because 1 minus sine squared is cosine squared, square root of cosine squared is cosine. And then dt is 6 times cosine of theta d theta. Now there are going to be a lot of trig sub problems where you do have to do this square root of a square thing. And if they don't tell you limits of integration, you just assume that the square root of cosine squared is cosine. If there was going to be some shenanigans, they would somehow have to give you some extra information. So we just assume square root of x squared is x. All right, if it's not given otherwise, that's what we're going to assume. So is everybody clear that this becomes cosine squared, and then square root of cosine squared is cosine? Cosine times cosine is cosine squared. So the evaluation of this whole square root, this all becomes equal to cosine of theta. And then, once again, how do we evaluate an integral with a sine squared or a cosine squared? Power reduction identity. We need to reduce that power. Let's come over here. So both power reduction identities have a division by 2. So we'll pull the division by 2 out in front as a coefficient. And then cosine squared is 1 plus cosine of 2 theta. So 1 plus cosine 2 theta over 2. So this will give us 18. We can now integrate. The integral of 1 is theta. Integral of cosine is sine. Then we have to do reverse chain rule. So we have that. So these sort of steps you're going to see again and again, where you end up with sine of 2 theta. We have to use the double angle identity. I'm going to distribute that 18. So that's going to be 18 theta plus. So here, sine of 2 theta is 2 sine theta cosine theta. So the 2's are going to cancel. So that 18 is going to come over here, and we're going to have sine of theta cosine of theta plus c. So sine of theta plus cosine of theta, sine of theta times cosine of theta plus c.
Why is it not 9?
Because this becomes 2 sine theta cosine theta. And these 2's are canceling.
How does that work? Why is it turned sine and cosine?
That's the double angle identity for sine. So sine of 2 theta is 2 sine theta cosine theta. That one is... Okay, so now we're sort of at the end. We want to get back to the original variable, which in this case is t. So this is where we draw our magic triangle. So our magic triangle, this is the triangle that takes us back and forth between thetas and x's. We look at our original substitution. Sine of theta is t over 6. So we set this triangle up. It looks like we're in quadrant 1 of the unit circle. Always draw it the same way. Always draw it like it's in quadrant 1. And that original substitution is going to have 2 of your sides automatically. We're going to have one missing side. And that missing side we calculate with the Pythagorean theorem. So this will be the square root of 36 minus t squared. And it should be that you get either identically what's in the integral somewhere or something really close for that missing side. And once you have this magic triangle done, now it doesn't matter what trig function. If it's a sine, if it's a cosine, if it's a tangent, everything comes from here. Cosecant, secant, all the trig functions are now right here. And let's go for it then. So our final, let's see, we have 18 theta. So notice up here, this is where we can isolate theta. To isolate theta, we take the inverse sine of both sides. So theta is going to be the inverse sine of t divided by 6. All right, so let's substitute. So we get 18 inverse sine of t over 6 plus 18 sine theta cosine theta. So sine of theta is t over 6. Cosine theta is adjacent over hypotenuse, so that's going to be root 36 minus t squared divided by 6 plus c. And all we can do is simplify this a tiny bit. So we're going to have the 18 sine inverse of t over 6, and then plus
1/2.
half,
18 over 36.
all that stuff. And there we have it. Is that making sense to everybody? Ooh. So a lot of steps in there.
On that last part, how'd you get 36 minus t squared over 6? Square root.
So this is cosine of theta right there. And cosine of theta is adjacent over hypotenuse. So that triangle that we build it from our original substitution step. It's always going to give us two of the sides, and then we figure out that third side, and then we can go back to x or t or whatever. We can go back to the original variable. Other steps there you want to ask about? So this is a common feature also. Sine of 2 theta, we don't know what sine of 2 theta is. This triangle only gives us information about single theta. So we've got to use a trig identity to get that double angle broken apart. So, yep.
That's like, so we're doing the identities to just get like sines and cosines?
Yes,
Any way we can?
of single theta.
Okay.
Yep. Because our original substitution is with just theta, not 2 theta. So we've got to somehow break, anytime we see a 2 theta, we need to break it apart into single thetas.
And you don't always need to go all the way to sine and cosine. You can also use tangents and secants and all that.
As long as we have just
As
single
long as it's
theta.
a single theta.
Yep,
It doesn't matter.
doesn't matter. All right, let's try one other than sine.
Oh boy.
Okay. So these ones are the easiest ones. It's just easy to remember that if there's a plus, tangent starts with a t, it looks like a plus. Right? Tangent is the identity that we always use if we have a plus. So, let's do it this way. Let's do this one first. This one's harder, and then I'll let you guys try that one. So let's go with this one first, which is also a tangent, but there's a little bit more work because this is a sum of squares without a 1, and this is already a sum of squares with a leading 1, so that's already set up nicely. So that's going to be a little easier. So let me do this more complicated one. So the first step is that what we want is to have a 1. So we want to, come on. So, So we want to have a 1 in here instead of a 36. So we're going to factor so that we end up with the sum of squares, in this case with a trailing one. Doesn't really matter for sums of squares, whether it's a trailing or a leading one, that's just your preference. For a difference of squares, that matters, but sum of squares does not. Okay, so that 36 is going to be factored out. And let's see if we can do it without writing that intermediate step of 36 over 36 here. What you should start to see is that when you factor out whatever it happens to be, it introduces a denominator in the term that doesn't have anything there. So that 36 is coming out to the front as what? 36 squared. Why is it being so finicky there? 36 squared. Right, so whatever the power is, it has to come along as you factor it out. Remember when we had the square root, we pulled out, if we pull the 36 through the square root, it turned into a 6. So that power of 1/2 came along as we factored it out. So in the last two, we were coming through a square root, so that square root had to be taken of the number. Here, instead of a square root, we have a square, so it has to come with it. So we're factoring that out. The numerator is still z squared. Didn't do anything with the numerator. And down here, all right, let's see if we can, my gosh, why is it so finicky? So, 36 comes out of 36, leaving a 1. Now there's no 36 with that z squared, so it plops a 36 into the denominator, but then we want to write it as a single square, so we're going to write it as z over 6 quantity squared, yes. So there is the algebra step. And then, of course, if you need to write that 36 over 36 right here, just do it. There's the 36 over 36, and it's the numerator 36 here that's coming out and creating all that. All right, so we're pulling out 36. It's coming through the square, so the square comes with it. It's in the denominator. And then we have z squared over 36, which turns into z over 6 quantity squared. And now we ask the question, sine, secant, or tangent. And again, it's tangent because it's a plus. So z divided by 6, we're going to turn that into tangent. If you want to, you don't have to, it does not matter. You could isolate the z if you want to do that, if it's easier for you to differentiate without a constant in front of it. Do that, it does not matter. Your choice. And now we differentiate, and we're going to get dz equals 6 secant squared of theta d theta. And while we're at it right here, I'm just going to build the triangle right away, just for the heck of it. It does not matter when you do it. If we want to do it right away, we can, because I can still see this here. So tangent of theta is z over 6. So z and 6 are those two sides. Tangent is opposite over adjacent. Always build that triangle as if it's in quadrant 1. Your substitution step is going to give you 2 of the sides. That makes the hypotenuse here the square root of z squared plus 36. Order does not matter when you're adding. So that would be our missing side. Okay. So now we're ready for the substitution. So we're going to leave the 1 over 36 squared. Hopefully we'll get some cancellation at some point. We don't have to square that out. We'll find out. Limits of integration. Again, let's just go back. We'll just put placeholders in here for now. You could evaluate if you want, but let's just use placeholders because sometimes you don't have to evaluate an inverse trig function. So let's see, z squared. So there's z. If we square it, we get 36 times tangent of theta. So that is the numerator.
36 tan squared.
Tan squared of that.
Tan squared, thank you. Yeah, we're doing z squared, so 36 tan squared. And the dz is 6 times secant squared of theta d theta. We'll put that on the outside. All right, so there's our numerator. In the denominator, we're going to have tan squared plus 1 squared. So tan squared of theta plus 1 quantity squared. So a bunch of cancellation here. We're going to get one of the 36's to cancel. And then we're going to have 6 over 36, which is 1 over 6. So constant out in front becomes just 1/6. Now our identity, this inside here is secant squared. Tan squared plus 1 is secant squared. So that makes the denominator secant to the 4th. And if we have a secant squared in the numerator, 2 of them will cancel, leaving us with secant squared in the denominator. So numerator, we will have tangent squared of theta. And in the denominator, when all is said and done, we'll have a secant squared of theta. So we've got that. So denominator is secant to the 4th, numerator is secant squared, a pair of secants cancel, leaving a pair in the bottom. 2 over 4 is a half. We have 2 in the bottom. So we have powers of secant and tangent. Those powers of secant don't count as even because they're in the bottom. They're not in the numerator. And that power on tangent is not odd, so we can't use either of those 2 techniques. Then we go to Pythagorean theorem. So if we rewrite tangent squared, let's see if it helps. So tangent squared, okay, tangent again, memorizing that triangle is key. So tangent is on this side, secant is on the hypotenuse, 1 is down there. So tan squared is secant squared minus 1. Over secant squared. Now we can split the fraction. And let me just point out again that fundamental feature of trigonometric substitution, our denominator had, these 2 terms down here, and once we did the trig sub, those 2 terms merged into 1 term, and when the denominator is 1 term, you're good because then you can split the fraction. So that's one of the hallmarks of trig sub, is that you're collapsing 2 terms down into 1. So now we're going to distribute that denominator, i.e. split the fraction. So we're going to have 1/6, and when we split the fraction, secant squared into secant squared is 1. Secant squared into 1, so the reciprocal of secant squared is cosine squared. And what's 1 minus cosine squared?
Sine squared.
Sine squared. All right, we're getting there. And if you didn't notice that, you could integrate that right where it's at, but it's going to be easier to reduce it all the way down to sine squared. Which, now that I look at it a little more carefully, right here, if you turned everything into sines and cosines, you would have got there a little quicker, which is how trig identities work. Sometimes you see the fastest way, sometimes you don't. You need to sort of do what you know is true. I know that that's true, and I could see that that would split. But if you turned it into sines and cosines right away, that's sine squared over cosine squared, that's 1 over cosine squared, the cosine squareds get flipped and canceled. It would have been quicker. But it's not always obvious with trig subs, with trig identities. All right, now we use power reduction.
Power reduction.
Power reduction again. So power reduction, the half comes out to the front, making a 1 over 12 integral. And inside here, we have 1 minus cosine of 2 theta, d theta. And we integrate. The integral of 1 is theta. The integral of cosine is sine. We have to use reverse chain rule. Whoops, not a plus c. We have limits of integration. So we just have our placeholder limits still. Sine of 2 theta, again, very important double angle identity. We've done, it's been in every single problem we've done so far. So 1/12 theta minus sine of 2 theta is 2 sine theta cosine theta
Over 2.
over 2, so the 2's cancel. So those 2's are gone. All right. Now we're back down to just thetas. That's where we want to be. Now we can use our triangle to get from theta back to x's or t's or z's or whatever the original letter was. So we will have 1/12. So if you look at your original, that's how you isolate theta. You inverse tangent both sides. So theta will be the inverse tangent of z over 6. Everybody okay with that? So we inverse tangent both sides, leaving us just theta on the right-hand side. And now we can plug and chug. So theta, inverse tangent of z divided by 6 minus sine of theta, we go to the triangle. Sine of theta is opposite over hypotenuse, so z divided by the square root. So z over square root of z squared plus 36. Cosine, go to the triangle. Cosine is adjacent over the hypotenuse. So we're going to have 6 over that square root. Messy in there. Okay. Limits of integration. We're back to our originals now, which I have no memory of whatsoever.
6√3
Oh.
top and 6 bottom.
Not great, huh? 6 and 6√3. All right. So let's pause for a minute. Any questions up to that moment? Let's get our inverse trig evaluations going then. So we have a 12th out in front. We'll just leave that as a coefficient for now. We'll deal with it in the end. So substituting 6√3 across the board for the z's. Starting here, we get inverse tangent of √3. Nope.
Doesn't have a nice name.
I don't know. Is there a reason why we didn't multiply the?
These two? Yeah, we can do that. We can simplify that. When we're doing the evaluation, we can kind of do it in our head, but you could write it out. Like if we had an indefinite integral that just had a plus c, we would definitely combine those right away. Yeah.
5/3. Yeah, it's 5/3.
5/3, yes.
Yeah. Yeah.
So let's go back to unit circles for a second. If this is not jumping out at you, I've written this on the board before, but let's do it again because it's really, really important. because it comes up so freaking much. So let's take that circle. Knowing your tangent ones is really helpful. So let's put that down here. Slope is tangent. All right, tangent is rise over run. It's y over x. If you're dealing with terminal rays that go through the origin, slope and tangent are the same. When you look at the slope right here, the slope, so I think of this in my mind as this, good grief, you're driving me crazy today. I think of that as this on the 12 sector circle. The 8 sector circle is simple, right? The slopes are -1 and +1 for the two intermediates. But for this one, we have a steep one and we have a less steep one. But there's only two. One's steep, one's less steep. And slope is rise over run, it's y over x. If you do √3 over 2 divided by 1/2, the 2's cancel, you get √3. That steeper terminal ray is square root of 3. The less steep terminal ray, same thing, slope is y over x. So it's y divided by x. The 2's cancel, you get 1 over √3. And then if you rationalize the denominator, you get √3 over 3. So the steep terminal ray is at √3. The less steep one is √3 over 3. It's a third as steep.
And also to simplify, this less steep one is just inverse of the steeper one. 'Cause there's only
The
two.
reciprocal of it, yeah. Yep. Truth. So that tells us that, so right over here, let's get rid of this. So right over here, inverse tangent of √3, that's the angle with the steeper terminal ray. That's pi over 3. So we're going to put a pi over 3 in right there. And then we come over here, and in the numerator, we're going to have 36 √3. So subtract off 36 √3. And in the denominator, we have a root times a root, so the root vanishes, and we just have what's inside. So 36 squared plus, z squared plus 36, that's going to be, if we square that, we get 36 times 3. 36 times 3 plus 36. So 36 multiplied by 3 plus 36. That's the denominator. So we can factor that out. We're going to end up with 144. Okay, now we subtract off antiderivative at 0. Plug in the 0 here. Inverse tangent is 0.
It's not 0,
Six.
it's 1.
Say again?
1, 6.
Your lower bound is 6.
Your lower bound is 6.
Not 0.
It's
Not
6
zero.
over 6 is
Oh, thank you.
Yeah,
It's
yeah.
not 0.
Yeah.
Wishful thinking.
I know.
It'd be easier.
Nice.
Although inverse tangent of 1's pretty easy.
Yeah.
Inverse tangent of 1, angle on the right with a tangent of 1, angle on the right with a slope of 1, pi over 4. So pi over 4. And now we're subtracting a negative, so we get plus. 6 goes in here, we get 36 in the numerator. Denominator, the square root goes away, and we have 36 plus 36, which is 72.
Which is 1/2.
Which is a half. So we are almost there. Yeah, these problems are not short. So let's combine the pi's. This is going to be 4 minus 3, which is 1 pi over 12. You should also be able to visualize that from the unit circle. If you're looking at the unit circle, there's so much visualization that goes on with this stuff. If you're looking at this unit circle, the little differences are pi over 12s. Right? So if you were to draw a a unit circle that, good grief, today it is, why is it so finicky today? So if you were to draw I'm gonna swear. If you were to draw those intermediate spots right there, so if you were to draw that spot and that spot, then all of these distances would be pi over 12s, right? So if you do pi over 3 minus pi over 4, you get pi over 12, right? It's one of the little slices. If you were to do pi over 4 minus pi over 6, it's a little slice, it's pi over 12. You know, so you can do it that, visually you should be sort of seeing that. Obviously, you can just do common denominator stuff and make it 4 pi over 12 and 3 pi over 12 and take the difference and get 1 pi over 12. But it's good to start visualizing those angles. Okay, so we've combined those. And then this 36, we can just wipe this out, right? That goes in there once, goes into there once, and it goes into there once.
Root 3 over 4.
So we get root 3 over 4. So minus root 3 over 4. And we said this is a half, which we'll write as 2/4. Then we're almost done. We're going to get pi over 144. And then here, this is going to be 2 minus root 3 over 4.
48.
So 2 minus root 3 over 4 times 12, which is 48. So there's, as far as anyone would want to go.
I used to think solving a quadratic equation with a quadratic formula took a long time.
Doesn't that seem like child's play now? After solving trig subproblems.
Basically finding the zeros of, let's say, y equals 3x squared minus 2x plus 8.
Child's play. Yeah, it's amazing how the more mathematically mature you get, you look back at algebra, you look back at even the Calc 1 stuff sometimes, it's like, whoa.
And now we get to try it ourselves.
Now you get to try it yourself. So I'll give you the easier one, because I'm so kind. All right, so try that one with trigonometric substitution. Luckily, it's an indefinite integral. You don't have to deal with inverse trig function values.
Would you ever, for that last one, consider plugging back in for z's before you integrate, or would you always want to integrate first?
That's...
Because you could, once you get it to tan over secant or sine squared, you could then go back to z values there before integrating. I just don't know if that helps.
I don't know either, actually.
Like, I don't know if that gets you anywhere.
I feel like it
But-
should take you back to where we started.
I figured it might, but I was just looking at it.
Yeah.
It took a lot of.
Because we don't have a sine squared, so sine squared of theta. So sine is this over, yeah, would take us
Yeah,
back.
so that then takes you
It's
all
going
the
to
way
take us right back.
Okay.
Yeah,
Yeah,
Good,
alright.
good question.
I figured it.
Yeah. Yeah, it's going to take us right, yeah, it's going to take us right back.
Yeah. It's not gonna take you all the way back, but it takes you close enough.
So
Because you end up with,
but we're going to have to replace the d theta too.
oh, the d theta, that's
Yeah.
right. That's why it gets you all
That's
the way
why it
back.
gets you all the way back. Yeah.
Yeah, that makes sense. Okay.
Yeah, good question though.
You're how do you deal with the 3 halves though? Like, it's not a square.
It's not a square.
But secant squared to the 3 halves is
So what did you, let me see your substitution.
Yeah.
So you're gonna let x equal sine secant or tangent? So in this one, there's no factoring, so it's easier to you're just replacing x.
These two cancel, so that becomes.
So what are you gonna replace x with?
Tan theta.
Tangent. So your substitution step is x equals tangent of theta. So x equals tan theta, and now differentiate both sides of that x equals tan theta equation.
Cosine?
Yes, it is.
X equals tan theta.
Cosine of theta. Theta, and what are we gonna take our cosine?
So if you have a secant squared, that is one of our special cases, right? Secant squared, you could just let u equal, so secant squared, you can imagine the secant squared out with the differential. So your theme, if secant squared's out with the differential, is that you're gonna let u equal,
So it's secant squared to the 3
or u
halves.
sub. If you pull off secant squared, you're gonna let u be.
Would that equation simply
So we're gonna let x be tan theta, that's our first step. So we have this sum of squares, we wanna create a 1 plus tan squared, because we know 1 plus tan squared is secant squared. So we're gonna start with x equals tan theta, what's the derivative of tan?
So I'm trying to think, I don't know how.
Tangent.
Oh wait, maybe it's
Yes,
x over 1?
exactly.
I don't have plus C.
That's why I added it backwards.
So there's the first step up on the board. Hopefully you're past the first step on the other.
I'm not,
Oh, you're not? You're on
Or
zero?
use significantly less blood or you run the
yeah, this
risk
is gonna take a while.
for the copyright infringement checks. That
So
never
now
shows up.
substitute all that mess in. If you're coming against a brick wall, let me know and I can come give you a jackhammer.
Yeah, no, how do we figure out what C is? Where X equals 1? It's always been there. And my brain always thinks it's a concept, therefore it can be anything. So this doesn't happen. Oh, it's all C.
X over square root of C squared minus 1.
Oh, yeah, that's right.
If you want to
Yeah,
rationalize
that's
it.
right. 1 plus tan squared is secant. No, that is right.
algebra class.
I don't want to rationalize my denominator.
Thank you very
That's
much.
more complicated.
Oh, they already did it.
You're simplifying properly?
There's a day. It was, was it yesterday?
Yeah, something is fishy. Yeah, you don't need to go here. Yeah, this should simplify more.
He left it.
What does
It was pretty-
1 plus tan, what 1 plus tan squared
Our
is,
physics teachers.
right? Yeah, so you have a Pythagorean flaw, a p flaw. All right, so I'm going to substitute this in right now. So dx is secant squared of theta. Did my settings get changed?
Well, 1 over, it's 1 over C, not.
It could be this, but I'm huge also.
If it's 1 over secant, it's just cosine, and then you're just integrating cosine, and that's like 8,000% easier than natural.
Because 1/2 is square root and this could be. This is.
Wow.
Who's the?
Why is it doing that?
It's gonna be secant.
Are you like statically charged or something?
I don't know, maybe.
Around somewhere?
It's just really being so, it's been working so great overall.
does not have.
No, if you want to say
Oh my god.
X is equal to.
Neither is
Hold on.
Okay, secant squared of theta d theta.
Yeah, it's how,
So in the denominator, you have 1 plus tan squared, which is secant squared. And that's all raised to the 3/2 power. How does that denominator simplify? Secant cubed. So we should end up with,
next 6 square root.
it's been working so well, probably just have to reboot the computer to make it stop doing that.
Currently have the new line technician looking into the issue.
Oh, Tanner, what the hell's going on here?
New line technician's looking into it.
Makes you feel any better, Steve struggled with it all year.
I've had pluses and minuses, but this semester has been working better than ever since we changed that one setting.
The only thing I can think of is you're using the thicker marker, and Windows uses thickness of input to determine what you're doing. The thinner marker would make a bigger distinction between.
That's true.
Yeah.
That is true.
Yeah.
But with this setting turned off right here, this setting there where it's not automatically
Yes.
trying to detect it, it
Yeah.
shouldn't matter.
Yeah, it should be trying.
We're talking about Windows here.
Yes.
Yeah, that's true.
Yeah.
That's true.
Yeah.
That's a good strategy though, so if it's doing this, I could just do that. All right, so if we go here, everybody agree with that? This one's gonna unravel so nicely. Isn't this just the integral of cosine of theta?
Forgot to square the one.
And integral of cosine is sine of theta plus c. And then we're going to go to our magic triangle here. Takes us back and forth between thetas and whatever the other letter is. Come on, I want a better triangle than that. Gotta make that horizontal. Ah! Okay, tangent of theta is x over 1. So we're always going to put theta right into this little pocket right there as if it's in quadrant 1. The hypotenuse will be the square root of the sum of the squares, so square root of x squared plus 1. And then all we need is sine from that triangle. Sine is opposite over hypotenuse. So that's x divided by the square root of x squared plus 1 plus c.
This one,
It's almost like if you make this problem easier, there's no problem.
So if there's a 1 already, that makes it a lot easier. And this one just sort of, this one was so pleasant almost, right? It's like doing a harder, scarier one first makes this just feel like, I can do this after all.
I guess it depends on how nice you are with that.
Exactly.
That's the fun part.
All right, so let's try one with, are you starting to see what the substitution would be?
Yeah.
Is this one going to be sine, secant, or tangent?
Secant.
So tangent if we have a sum of squares. Sine if we have a difference of squares with a leading 1. This is essentially a difference of squares with a trailing 1, so this is going to be our third case. Now we are going to rewrite this. It's not truly a difference of squares yet, though. So in this numerator, we don't have to factor anything out. But it's not written as a difference of squares as it sits. So now it's written as a difference of squares. So it's a difference of squares with a trailing 1. Difference of squares is sine or secant. This one's going to be secant. So we're going to let 2x equals secant of theta. And then take the derivative of both sides. So the derivative of the left is 2, so we'll have 2 dx. Derivative of secant is secant theta tangent theta times d theta. Not bad. So as we convert all of our x's over, we will have, let's see, 2x we said is secant. So we're going to have the square root of secant squared of theta minus 1, all divided by x squared. So if you think about x down here, x is secant over 2. If you square that, you'll get secant squared over 4. And let's see, dx. dx here is going to be 1/2 times secant tangent. So we have that That's shenanigans.
Can you explain the over 4?
So if we isolate x, if we isolate x here, x is secant divided by 2. So secant over 2, quantity squared, secant squared over 4. So this is x squared. So that 4 actually pops up into the numerator. So we have a 4 over 2, which is 2 when all is said and done. How about secant squared minus 1?
That becomes tangent.
Tangent squared, and the square root of tangent squared is tangent. So the numerator, that square root part becomes just tangent. All right, and do you see that we can cancel one secant with the denominator?
Yes.
We have a secant in the numerator over here, and we have a pair of secants in the denominator, so one cancel. So we're left with a secant in the bottom. And then over here, we have another tangent that's going to multiply by this tangent, giving us tangent squared, and then d theta. All right, so any piece of that that you need an explanation for? Okay, so once again, we're in a position where we don't have secant to an even or tangent to an odd, so we can't use one of those two techniques. So usually we just go to Pythagorean theorem, but what also can work, as we saw in the last one like this, you could just turn to sines and cosines. One of those two things will work. Both will work. One will be faster than the other, most likely. So we could just convert to sines and cosines this time and just see what happens. Now that I did that switch with this pen just for a moment, now this thing is working fine again. Tangent squared is secant squared of theta. Oh, I said I was going to go to sines and cosines.
Yes.
So let's do that. Come on, go away. All right, so that's going to be... If you're going to sines and cosines, you could shortcut some of your notation and think of S as sine and C as cosine if you're only using sines and cosines. So you could write this as sine squared divided by cosine squared. That's tan squared. And then secant is 1 over cosine, which is going to put a cosine over 1 as your second factor.
Cosines cancel.
So the cosines cancel. And let's see. So then we'd be left with sine squared of theta over cosine of theta. Huh, that didn't help us too much. All it did, we still have a, it probably would have been better to go with
What you'll end up with now, because I was just doing this, is you now
1 minus cosine squared. And,
You're already doing it Pythagorean anyway.
Yeah.
You should have just done it with tangent.
yeah, we should have just done it with, we should have just rewrote tan squared as secant squared minus 1. And you don't know, it's not obvious which one's going to be faster,
Yeah.
usually.
You'll end up with numbers anyway.
Now,
You end up with secant.
yeah, so if we rewrite that
If I'm not insane.
as 1 minus cosine squared of theta divided by cosine of theta d theta, we end up with 2 times the integral of secant if we split the fraction. So when we split the fraction, we're going this way and this way. So if we split it to the left, we have 1 over cosine, which is secant. Splitting it to the right, we end up with cosine d theta. And that gives us, well, we're right where we want to be. We can integrate both those functions.
Secant's not fun, but livable.
So secant, remember, is natural log of absolute value of secant plus tangent. Minus the integral of cosine of sine. We'll distribute this 2 from the front. So we'll have that. We're almost there. So we've got to create a magic triangle over here. something to finish off the problem. So secant of theta is 2x. So this triangle is going back and forth between x and theta. It's a picture of the relationship between these two. So theta always goes right there. Secant is hypotenuse over adjacent. So the hypotenuse over the adjacent has to be equal to 2x. So that's going to be the simplest way to make hypotenuse over adjacent 2x. Which then makes this side, Pythagorean theorem, the square root of 4x squared minus 1. And now we can replace any trig function we see based on that triangle. That triangle gives us all the trig function values. So we have, let's go with secant first. So secant is hypotenuse over adjacent. So we're going to have 2 natural log absolute value 2x plus tangent square root of 4x squared minus 1 minus 2 times sine. Sine is opposite over hypotenuse. Opposite over hypotenuse. So we'll have a square root of 4x squared minus 1 over 2x. The 2's will cancel. So that 2 and that 2 cancel. And that is about as low as we can go. All right, any part of that you want to ask about? Trig sub. The hardest part of this chapter. And then we get to the easiest part of this chapter next. PFD, partial fraction decomposition.
It doesn't sound easy.
It's easier than it sounds. All right, any question on that? Yeah, these definitely take a little processing because they're complicated. Okay, so let's go. Let's at least get this one started. The chances of us finishing are, oh, I guess we have 10 minutes. We might be able to just barely finish it. So first step, we want to have a sum or difference of squares with a 1. That's always going to be easier. And so in that denominator, we want to factor the 64 out. So that 64 is in the denominator. And the power is a 1/2, right? We've got that root. So that 64 has to come to the front with whatever that power is, and it just so happens that we can actually evaluate that. So the square root of 64 is 8. So when we factor it out, we're going to have 1/8. We're going to have 8 root 2 to 16. dx in the numerator, and in the denominator, this is going to end up being x divided by 8, quantity squared, minus 1. Everybody see that? Right? When you're looking here and there's no 64, you're imagining 64 over 64 so that you can factor that 64 out, and then you're left with x squared over 64, which is x divided by 8, quantity squared. And then we say to ourselves, sine, secant, or tangent. We have a difference of squares with a trailing 1. Difference of squares with a trailing 1 is secant. So that x divided by 8 is going to be equal to secant of theta differentiate both sides. That'll give us a 1/8 dx is equal to secant theta tangent theta d theta. That is all we need to substitute. In the numerator, we have dx. So we look here and we mentally isolate dx. dx is going to be found by multiplying both sides by 8. So we're going to have 8 secant theta tangent theta times d theta. In the bottom, we have the square root of secant squared minus 1. We have a lot of cancellation here. The 8s cancel. Secant squared minus 1 is tan squared. But then we take the square root of tan squared, giving tan. And so that tan cancels with the numerator tan. So this is all equal to tangent. So that and that cancel. So this all boils down to, is it just the integral of secant, right?
You thought we might not finish.
Yeah, we're going to finish. So the natural log, absolute, secant plus tangent.
Let's see. No, we get,
You can see we come across this integral of secant all the time, so it's just good to know.
Not plus C, we have.
Oh, we have limits of integration. Oh,
don't listen to me.
thank you. Limits of integration. That's going to make it much more interesting, right? So right here we put our placeholders.
I just write A and B.
You can write A and B, you can write C and D, you can write Z and U, whatever
Or my
floats,
first and last name.
whatever floats your boat. As long as your boat's floating, things are good.
Would you mark us down if we left it as x equals 16 and x
No,
equals?
you could do that too.
Because then I don't have to go back to another page to write 15.
Yeah, totally fine. All right, so then we have our triangle here. Secant is hypotenuse over adjacent. We want secant to be x over 8. So we're going to do x here, 8 there. Theta is in the corner. Secant, opposite, secant is adjacent. Jeez. Secant is hypotenuse over adjacent, so we have that. Then we use the Pythagorean theorem to get square root x squared minus 64. It should look like something that's in the original or close to it. Now we're good to go. We can substitute. We can get all the way back to x. So we're going to have natural log, absolute value. Secant is x divided by 8 plus tangent. We get that over 8. And now we're back in the land of x's, whatever they were, 8 root 2 and 16. We have that. Okay. So let's plug in the 16 first. So we're going to have natural log, absolute value, 16 over 8 is 2. 16 squared, is that 256? So 256 minus 64. 256 minus 64, 192?
That's correct.
192, and that's going to be square root of 192, right?
So we're not.
Okay, so we've got that. Then we have to subtract off the natural log. Plug in 8 root 2, so we're going to have a root 2. And plug in 8 root 2 here. We're going to get 64 times 2, which is 128. 64. Isn't that 1?
Yes. If I did my math right.
With that,
Because you get 128 minus 64.
which is 64, square root of 64 is 8, yeah, okay. Agreed? Okay, so then 192, what does that factor into?
Pull out an 8 from it somehow. Because it should be 64 times 3.
It does, it turns into an 8
Power
root 3?
6.
8 root 3, okay, yeah.
Power 6 and then 3.
Okay, so 8 root 3, so it's going to end up being 2 plus root 3 minus natural log of root 2 plus 1, or if we write the square root second, looks like that. Then we can write it as 1 natural log. Natural log of the numerator would be 2 plus root 3. We don't need an absolute value, everything's positive. So that would be our final answer.
1 minute to spare. On to the next one.
So square root of 192 is 8 root 3. Yeah, 64 times 3 is 192.
Which we could have just done by 16 squared is 64 times 4.
Exactly.
And then
Back from the beginning.
minus of 64.
That's right. We had 3 of them left.
We have 3 left.
All right, any step on this one you want to ask about?
Why did we get rid of the absolute values? Is it
Because these are both positive numbers.
oh, that makes
So
sense.
the absolute value of positive number is itself. Yeah.
Are there questions on that one?
Since it's a definite integral, you don't have to worry about if there's 0.
All right, well, we'll stop there. Do your due diligence and do a bunch of integration by trig sub between now and Thursday.
Yeah.
So we can go over any questions you have on Thursday with the trig sub stuff. Questions from the homework or anything? Because these things just take a lot of practice.
Yep. And then just
A
get
whole lot of practice. All right, see y'all on Thursday.
Physics takes the bit. I think I need an hour break first.
Well, I'm increased then.